Hello everyone, thank you very much for coming. My name is Smbat. Today I'm going to present my capstone project, Educational Horn Antenna System. So today's agenda is going to be, first of all, the motivations. Why do I even care about this system? The system workflow overall and basic information about the system. Specifically, we will concentrate on three circuits. So first one is the transmitter circuit, is this part. Then we will talk about the receiver circuit, and we will talk about the audio amplification and audio presentation circuit. At the end, I will talk about future developments. What is the main motivation for this system? As name suggests, the educational improvement in Armenia is very important for me, specifically the field of wireless and telecommunication and radio engineering, RF engineering. So I've noticed that in high school and university, students are not motivated enough to deep dive into these essential fields. One reason that I can suggest that I also had during my high school years is the fact that these classes need visual or audio representation. When the theoretical part is presented to a student, it is very beneficial for him, and it is very motivating to see or hear the signal that he or she generates. So another important motivation is that overall RF and wireless educational toolkits are not very good presented in the market. So I have deep dived into the internet, and if I'm a student who wants to buy an educational toolkit for RF or wireless testing, first of all, either I will not be able to do that because the producer is only batch producing, or the price of the toolkit is varying from $1,000 up to $7,000 or $8,000. Last but not least, the wireless industry growth is very important during these 2 decades. Almost this year, wireless industry market capacity is almost $2.7 trillion. And one important aspect also in the military part is electronic warfare. That is very essential for nowadays technology development, and is very essential part for country's defense. So let's talk about the system workflow overall. The signal, this part is our transmitter circuit. The 10 GHz signal is being generated by the gun diode oscillator. As you can see on the left part, this is the modulator, which is going to modulate our initial carrier signal. After that, the signal is going to go through the waveguide. It is going to propagate into the space, and after propagation, we are going to our second circuit, the receiver part. After propagation, signal will be captured with the help of RF diode detector, and after that, we are going to take out the RF frequency from the signal, and we are only going to take the modulated signal, which is generated in here, and we are going to present it with, after 2 amplifications, with the loudspeaker. So the student can understand, can hear what he or she is generating here. So on left part, you can see simple power intensity to distance test. I took our 2 horn antennas. I've placed them approximately in 1.9 meters, and each step of measurement is 5 centimeters closer to the previous one. The graph, the scatter plot, is presented in a way of a voltage in squared with respect to distance, because when we are measuring the voltage in the receiver part, that voltage, the square of that voltage should be proportional to the power generated in the transmitter part. On the right part, you can see simple power intensity to angle visualization using MATLAB. red represents the maximum amount of power, maximum amount of dBs up to 12, and the blue part represents the least amount. As you can see from the directivity of the antenna, the red one is here and the blue one is the tail of the antenna. So let's concentrate now specifically on the generating circuit. So we are using GaN diode oscillator in here in order to provide the RF frequency. But before talking about the GaN diode oscillator, it is very essential to understand what is GaN diode and how it works at all. So GaN diode is a semiconductor device that has 3 layers. All 3 layers are n-doped created by n-doped semiconductor materials. And if we compare with a normal diode, normally diodes are being p-n junctions, but in this situation our GaN diode only has n junctions, 3 n-doped layers. The middle layer is less doped than the first and third layers. And usually the development of GaN diode is done by using gallium arsenide or indium phosphide. Those are the main 2 materials. Now, in order to understand what is happening in GaN diode oscillation, let's take a look at the energy level diagram of the GaN diode itself and what is happening when we are applying a voltage to the GaN diode. So in first picture, you can see that electrons are in their initial first energy level. After applying after applying a little amount of potentials, electrons are jumping from first to second energy level. After applying to the maximum voltage difference, we can see that the majority of electrons are now going upwards to the highest energy level. In this situation, electrons are becoming the speed of electrons is getting lesser, so the current within the diode is starting to attenuate. This is the effect. This is called a GaN effect, and the idea is that after even the third phase, that we are starting to increase the voltage, the higher level electrons are jumping back to the second level, and this oscillation is happening all the time within the diode. So this is called GaN effect. Also, this is called a negative resistance effect. So by negative resistance, we mean after increasing the voltage, our current is not increasing but decreasing. And after putting the GaN diode into a resonating cavity, which is this part, after putting the GaN diode into resonating cavity, and after applying the bias voltage, these oscillations are creating the given in this situation 10 GHz signal, and it is propagated through the waveguide. Let's now talk about the signal modulation here presented. We are going to use a simple NE555 timer module. This module is very popular because first of all it's cheap, it is for educational reasons. Second of all, you can actually modulate, you can actually change the duty cycle and the frequency of your modulated signal. Then the design is very simple, and you can generate from 1 Hz up to 500 kHz frequency, which is very good. Design is very simple. It has as you can see, 3 pins. One is simple VCC, one is the output pin, which is connected to the modulator. The output pin is the generated signal from the module to the modulator. And VCC is supplied usually from 5 to 15 volts. So what is happening during this modulation? First of all, we are doing amplitude modulation. Here we are generating a PWM signal. The generated signal in this situation is 1 kilohertz, and the duty cycle is 50%. So what is happening? When we are generating our carrier RF signal from a GaN diode oscillator, we can see that the top and bottom, the anode and cathode, are in y-axis, and the modulator is connected to the 90-degree perpendicular axis. So modulator is creating electrical field which is 90-degree perpendicular to the initial electrical field of the generated RF signal, and by that it is attenuating the it is attenuating when the when the signal of the modulator is in its peak, and it is amplifying the signal when the signal of the modulating is in its low. So we are taking our RF signal, we are putting the modulated signal on top of the RF signal, and we are getting the amplitude modulated signal through the waveguide. Let's now concentrate about the receiving. Let's now talk about the receiver circuit. So the modulated signal is being captured by the receiver antenna. After that, we in this part we have a simple RF diode detector. The simple diode detector circuit can be seen in this picture. What is happening in this situation? RF signal is coming. And due to the effect of diode, our signal is being half rectified, because diode is not letting the negative part of the signal to go back into the circuit. After rectifying our RF signal, we need to clean the signal from RF components and take only the modulated part that we are interested in. The cleaning is done by a very simple capacitor C1, due to the fact that the resistance, in this situation, the resistance of the capacitor is I'm sorry. Basically, the idea is that here we are getting a zero resistance for RF signals only, and we are cleaning the modulated signal by taking the output. After that, we are taking the signal and we are entering the amplification circuit. In this situation, I'm using TDA7050 module, which is low voltage mono stereo power amplifier. We are using specifically, there are two ways of using this amplifier. One is called a BTL application, and the second one is called a stereo application. BTL is opened as bridge tied load, and the idea of bridge tied load is amplifying the signal, amplifying the voltage that is coming from the signal, not twice but 4 times. Unfortunately now the system is not working in a correct way, so I took a video beforehand and I would like to show it to you how it works. This is the 1 kilohertz signal that you are hearing. This is a simple reflection test. This test is showing the polarity of the signal. And for the first test, we are taking the angles of both transmitter and receiver, and we are testing the reflection of the signal. So future developments of this project. First of all, it would be very good for visual representation also. We can use Arduino and simple coding to take the signal which is amplified after the amplifier module. We can also create a compact box for putting different parts in one single location. Obviously, we need in this situation quality cable management, and we can actually use different sorts of antennas, not only horn, pyramidical shape antennas. Those are my references, and thank you very much. Yes, please.
How do you do the modulation? You just wiring them together?
The modulation?
Yeah.
No. So actually, as you can see here, the modulator is connected to the is 90-degree perpendicular to the generated electrical field of the GaN diode. So when we are putting a 90-degree perpendicular electrical fields, one is attenuating the other, obviously. And when the modulated signal pulse is having its maximum amplitude, in that time our end modulated signal is having the attenuations. When the, yes, this one,
yeah.
yes,
Okay.
this is the yes, this is the modulation. Yes, yes, yes. Yes, please.
Thank you for the presentation.
Thank you very much.
A very simple question. What did you do to the device that... What did you do to the device that it stopped working?
Yeah.
And how to avoid it in the future?
Yes. So I can present actually. I can visually present what is not working in here. Okay, maybe I cannot, but I'll try. Okay. So yeah, the problem is either the amplifier circuit, or I believe that it can be connected to the capacitance, because when I started the system, I was getting waves that I should not get. So I thought that maybe the capacitor is not fully connected. So RF signal is going back into the receiver part, but it should not go. The RF signal should be fully filtered. It's either the amplification or the RF signal. So the the easiest way to fix it is to learn soldering better, and but the hard way is to maybe create a separate box for each component and like solder perfectly one time and don't touch it ever. Yeah. Thank you very much.
I have a stupid question.
No question is stupid.
Why 10? What's special about 10 gigahertz?
It's actually nothing special. It's called the X band. It is like from 9 to 12 gigahertz. There's nothing special in 10 gigahertz. Just as you can see from the shape of this, those are very old antennas. They are like developed in 1975. So it's the first like wave of antenna development, and there is a good book called GaN Duplexer Cookbook. The main idea is that it is the easiest frequency to get the waveguide like sizes in a correct way, and also in this situation actually 10 gigahertz can be related to the GaN diode oscillator, because the the frequency is not only dependent on the size of the waveguide, but also the generator itself. So there is actually nothing special. Yes, please.
Yeah. Is this on? Yes. On the receiver, yeah.
Yes.
Does the wave go directly into the transformer, or do you have something in between?
Does the wave go directly into the transformer, or I have something in between?
Yes. Is there
So-
anything there, or just go? It's
you
that's
mean
the
this
receiving
part?
antenna. Is
You mean this part?
yes,
No, this is simply the waveguide.
right.
And
But at the end, there's a transformer, right?
yes, in the end, this not the transformer, but the RF detector. So it is simple diode, like placed in this way. It's like simple diode placed in this way, and when the RF signal is coming through the waveguide, it is rectifying the signal, and you are taking the signal from here. So there's actually nothing in between here.
Yeah, that's
There's
the,
only waveguide.
Yeah, I'm just.
Yes.
Where's the transformer?
This?
Yeah, where's the on the receiving side the transformer, the IF transformer? You said, right?
Not the transformer, but like a simple diode detector. It is transformer, but it is simple diode.
Okay.
It is a simple diode circuit. They are called like RF diode detectors. They are. Yeah.
That's it.
Yes.
That's all I want to know.
Yes, please.
Thank you.
Thank you very much. Thank you.